The next lesson in our reaction and stoichiometry unit is on limiting reactants. Here are the two learning targets for this lesson, the first of which we want to determine the limiting reactant in a reaction. Before we get to actually looking at an actual reaction and determining the limiting reactant, let's take a look at a scenario that we might be a little more familiar with. Let's say that you're going to make some ham sandwiches for a party. Each of your sandwiches will use 2 slices of bread, 1 ounce of ham, and 0.75 tablespoons of mayonnaise. So you gather all of your supplies and you find that you have the following. You have 13 slices of bread, 5 ounces of ham, and 20 tablespoons of mayonnaise. Now I want you to ask yourself the question, how many sandwiches can you make? Go ahead and consider that for a moment. I suppose you've had a chance to think about this now, and the answer is 5. You could make 5 sandwiches. The reason being is after you've made your 5th sandwich, you've run out of ham. Notice that each sandwich will contain 1 ounce of ham, and you have 5 ounces, so once you make your 5th sandwich, you're out of ham. So this reaction, if you will, or the process of making sandwiches, it has to stop once one of the reactants, in this case the ham, if you consider those to be reactants, once it runs out, the reaction must stop. In other words, what we're saying here is that the ham is limiting in this scenario. And then we would have bread and we have mayonnaise left over. We would say that those are in excess. We have more than we need for this scenario because we can only make 5 sandwiches anyway. It wouldn't matter if I had 13 slices of bread or 13,000 slices of bread. I can only make 5 sandwiches. So what we're saying here is a limiting reactant is a reactant that is completely consumed in a reaction. This phrase, completely consumed, means it will run out. There will be none of it left over at the end of the reaction. And as we just saw with the sandwich example, this limiting reactant will determine the amount of product that can form, because once that limiting reactant is consumed, the reaction stops. Now, in an actual chemical reaction, it's determined by the mole-to-mole ratio in the balanced equation. That's how we would determine what the limiting reactant is. Any other reactant that's not limiting would be in excess. These would be reactants that are not completely consumed in a reaction. In other words, there's going to be some leftover amount once that limiting reactant is consumed. So let's take a look at an actual example of determining the limiting reactant in a reaction. Let's consider the reaction for the formation of water. We're told that we have 4 grams of hydrogen, H2, and we are reacting that with 64 grams of oxygen. And the question is, which reactant is limiting? Well, here's what we know from our analogy with the ham sandwich. We know that the limiting reactant is a reactant that runs out first. In other words, it will produce the least amount of product. So one way of determining what the limiting reactant is without having to learn a new problem-solving method would simply be to use those stoichiometry calculations that we've learned about to calculate the amount of product that each of the reactants could produce if it all reacted. Notice here in this statement, the could and the if are italicized, are also in bold here to emphasize that we're not saying that both of these reactants will produce this amount of reactant. We're saying it could produce it if all of that reactant did actually react. So we're just going to do a couple of gram, mole, mole, gram problems here. For each of them, I am going to calculate the mass of water, because notice water is the product. I'm going to calculate the mass of water that we can get if all of the reactant of that particular reactant did in fact react. So I'll just do the hydrogen first, just because it's listed first in the problem here. So I'm going to figure out how much water can be produced if all 4 grams of hydrogen react. So this is just a gram, mole, mole, gram problem. Converting from my mass of hydrogen to moles using the molar mass, 2.02 grams per mole. Then I want to use the mole ratio. Notice I have 2 moles of hydrogen for every 2 moles of water. So my moles of hydrogen cancel. Now I need to use the molar mass of water. Every mole of water has a mass of 18.02 grams, and this gives me 36 grams of water. Now what did I just learn? Here's what I learned. If all 4 grams of hydrogen do react, we would get 36 grams of water produced. I don't know for sure that that's going to happen, but that's what would happen if it all reacted. Now I need to do the same thing with the oxygen. Again, I want to find how much water is going to be produced if all 64 grams of oxygen react. So I use the molar mass of oxygen, it's 32 grams per mole. Grams cancel. Use my mole ratio. You can see up here 2 moles of water for every 1 mole of oxygen. And then I can use my molar mass, 18.02 grams per mole. Moles cancel. This gives me 72 grams of water. Well, what does this tell me? It tells me that if all 64 grams of oxygen react, we will get 72 grams of water produced. Now that we've done these two calculations, I want you to pause the video and think about this question. Which of these reactants, hydrogen or oxygen, is limiting? Alright, I assume you've had a chance to think this over. What we've learned here, and this is just what we learned from the last video, 4 grams of hydrogen react, we get 36 grams of water. 64 grams of oxygen react, we get 72 grams of water. This should lead you to determining that the hydrogen is limiting. The reason we know that is it will produce the least amount of product. In other words, once we get to 36 grams, once we get to 36 grams of water, there's no hydrogen left. It's all gone because all 4 grams reacted. So hydrogen is limiting because it will produce the least amount of product. So in other words, we're saying it runs out first. Now, another question we could ask would be what mass of water can be produced? Well, we've really already done that calculation. Based on our calculations up here above with the limiting reactant, we know that 36 grams of water can be produced because it's the limiting reactant that makes this determination. I know 4 grams of water is limiting. That'll give us 36 grams of water. So 36 grams of water is our amount of water that can be produced. Alright, so there's an example of determining the limiting reactant in a reaction. Now we'll look at this second learning target here. We want to determine the amount of excess reactant that remains in a reaction. So we're going to go with the same reaction, the formation of water from hydrogen and oxygen, and recall that we reacted 4 grams of hydrogen with 64 grams of oxygen, and that the hydrogen was limiting from our last example. Now we're going to ask the question, or we want to know the mass of excess reactant that remains. Well, the fact that hydrogen is limiting means that the oxygen must be in excess. In other words, there's going to be some left over once all the hydrogen runs out. That, by definition, makes it an excess reactant. So if we want to determine how much remains, we need to figure out how much of that oxygen reacted in the first place. So we're just going to do another gram, mole, mole, gram problem. We want to know the mass of O2 that are going to react with 4 grams of hydrogen. So just another gram, mole, mole, gram. We use our molar mass of hydrogen to convert it to moles. Our mole to mole ratio, 2 moles of hydrogen to 1 mole of oxygen. You can see there. And then we use our molar mass, 32 grams per mole for oxygen. And this gives us 32 grams of oxygen. Now notice I've emphasized this by writing the word reactant or reacted after this. In other words, what we're saying is we know all 4 grams of hydrogen will react because it is the limiting reactant. So 32 grams of oxygen will react along with it. Now that was not the question we were asked though. We were not asked to find how much reacted. We want to know how much remains, how much is left over. So to do this, we just need to subtract it from the initial amount of the oxygen. So I have 64 grams of oxygen that we started with, minus the 32 grams that reacted. This does give us 32 grams of oxygen that are left over. It just so happens in this example that the mass that reacted was the same as the amount that was left over. That is just happenstance. You do need to do the subtraction to figure out how much is left over. Alright, so we've seen how we can find a limiting reactant. We have seen how we can determine how much excess is left over. I have a couple more examples here that allow you to practice. As always, go ahead and read the problem. Pause the video once you see the question, and then try to work it yourself. Alright, consider the reaction. P4 plus 5 moles of O2 gives us P4O10. Here's the question. If 25 grams of P4 and 50 grams of O2 are reacted, what mass of P4O10 is produced? Even though this question does not ask us to do so, we must first determine the limiting reactant to know how much product can be produced. The reason this is I do not know which of these, the 25 grams of the phosphorus or the 50 grams of oxygen, I don't know which one is going to determine the amount of product that we can produce. In other words, I don't know which one's going to run out first. We need to determine that even though the question does not ask us for this. So to do this, we are going to find the mass of P4O10 that the phosphorus could produce if it all reacted. Then we'll do the same thing, determine the mass of P4O10 that could be produced if all of the oxygen reacted. So again, this is just a couple of gram, mole, mole, gram problems. We have 25 grams of P4. Use the molar mass to convert that into moles. Then I can use the mole to mole ratio. Notice the equation up here. The balance equation shows us that it's 1 to 1. And then the molar mass of P4O10. This gives us 57.3 grams of P4O10. Now remember what this tells us. This tells us if all of the phosphorus, all 25 grams of it react, we will get 57.3 grams of the tetraphosphorus decoxide, that would be the name of that, produced. We need to do the same calculation with the oxygen. How much P4O10 can we get if all 50 grams of O2 react? So again, a gram, mole, mole, gram problem, converting from grams to moles of oxygen using the molar mass. Then our balanced equation showed us we have a 5 to 1 mole to mole ratio. Then we have 283.92 grams for our molar mass again, as we did before. And this gives us 88.7 grams of P4O10. So what we've determined here is we know that P4 is limiting. The reason we know that is because it will produce less product than if all the oxygen reacted. Looking at these numbers, we can answer our question here, what mass of P4O10 is produced? 57.3 grams of P4O10 can be produced. We can see that from our calculation here with the limiting reactant. Same situation, but now we're asked a different question. What mass of excess reactant remains? The fact that we know P4 is limiting from the previous slide tells us that O2 is in excess. So what we want to do is we want to find the mass of O2 that reacted, then we can figure out how much is left over. So we want to know what mass of O2 is going to react with 25 grams of P4. Why start with the 25 grams of P4? Because that's the limiting reactant. We just determined that in the previous example, so we know that will determine how much oxygen will react along with it. So again, this is just another gram, mole, mole, gram problem. Using your molar mass, converting to moles, and then using your mole to mole ratio to go to oxygen. Notice the 5 to 1 ratio. And then finally we can use the molar mass of oxygen. This tells us that 32.3 grams of O2 reacted. To figure out how much is left over, we need to subtract that from the initial amount. We started with 50.0 grams of O2, 32.3 grams of O2 reacted. That tells us that 17.7 grams of O2 are left over. Okay, one more practice here. Just click through the questions. So you're told to consider the reaction between sodium bicarbonate and hydrochloric acid. And we're told that 1.82 grams of HCl are reacted with 2.01 grams of NaHCO3. And then 3 questions you need to answer here. Determine the limiting reactant. What mass of CO2 is produced? Calculate the mass of the excess reactant remaining. So again, pause the video, try it yourself, see how you do. One thing you might be wondering here, as far as determining the limiting reactant, is on the previous 2 examples, those reactions simply had one product. So what we did is we found which reactant would give us the least amount of that product, and that told us what the limiting reactant was. You'll notice here, there are 3 products, so you might be wondering, well, which one do I use? Well, this is why it's helpful to read through all the questions. Notice question B asks us what mass of CO2 is produced. So I'm going to need to figure out the mass of CO2 that we can make. So when I do this calculation, I am going to find the mass of CO2 that the HCl will give us. I'll also find out how much CO2 that the sodium bicarbonate will give us. This way I can kind of kill two birds with one stone, so to speak. So I want to use a gram mole mole gram calculation, converting from our mass of HCl into a mass of CO2. So just clicking through each step here, using the molar mass of HCl, that gets us to moles. Notice we have a 1-to-1 mole ratio here, HCl to CO2. And then the molar mass of CO2 is 44.01 grams. So that gives us 2.20 grams of CO2. I need to do the same thing with the other reactant, the sodium bicarbonate. So what mass of CO2 are we going to get from 2.01 grams of sodium bicarbonate? Gram mole mole gram problem, using the molar mass of sodium bicarbonate, then our mole to mole ratio, and then again the molar mass of CO2. This gives us 1.05 grams of CO2. At this point, we've really determined or answered these first two questions. Determine the limiting reactant and what mass of CO2 is produced. From my calculation here, I can see that the sodium bicarbonate will give us the least amount of product. So I know that the sodium bicarbonate is limiting, and I also know that 1.05 grams of CO2 get produced because that's how much limiting reactant allows for here. So I've answered those first two questions. Question C, calculate the mass of the excess reactant remaining. So the fact that I know that the sodium bicarbonate is limiting, I want to start with that, and I want to figure out how much hydrochloric acid reacted along with it. So I want to use the molar mass of sodium bicarbonate. This converts from grams to moles. Then I'm going to use my mole to mole ratio from the equation, use the molar mass as we're familiar with by now, and this tells us that 0.872 grams of HCl reacted. Remember, that is not answering the question. The question asks us for the mass of excess that remains. So I want to subtract that from the mass we started with. We started with 1.82 grams of hydrochloric acid minus the 0.872 that reacted, and this gives us 0.95 grams of HCl remaining. So we have answered our three questions. Alright, just to summarize what we've seen here. In learning about limiting reactants, we know that the limiting reactant is the reactant that is completely consumed in a chemical reaction. We know it determines the amount of product that can be produced, and it also determines the amount of excess reactant that remains. Recall, to calculate all of these, we simply need to do some stoichiometry calculations, some gram mole mole gram calculations, if you will, to determine which reactant will give us the least amount of product. That tells us the amount of product that can be produced. From that would tell us the excess reactant. We can figure out how much of that reacts along with it in order to determine the amount that remains.